We have info on the orders that we can talk about now that I'm ready.
Yes.
Okay, and how do we tell the orders if we're given these structure types? What do we do? Yep. So these are really representing this joint cycles. If they were not disjoint, then I can't take the LCM between the lengths of all of these. It will not give me the correct answer. But all of these are in disjoint form, right? And right, we don't have any missing pieces here as well, which is why we have those fixed points as well, the ones with the ones showing up on here. So here, all we have to do is take the LCMs of the lengths, which is exactly the numbers that are showing up on top of the underline here. So can you guys tell me the orders of these in the specific order? If we get 6. What do we get 4? 4 again. Great. Okay, any questions on how we got the LCMs for these numbers here? Right, we're very used to finding GCDs, so these might feel a little bit slower to decide what's the smallest multiple between the two. The thing that we'll notice is that when the GCD is 1, when they have nothing in common, then their smallest multiple has to be the product between the two. We have this, right, in general, if I had A times B, this is the same as my GCD times my LCM. So if I know my GCD is 1, then my LCM has to be the product between the two. And in terms of the powers of the primes, for my GCD, am I taking the min or the max? For my LCM, am I taking the min or the max in terms of the powers? Say it louder. Okay, let's think about this. If I had, right, my 4 and 2. Okay, here, what is my GCD of these two numbers? 2. This is the biggest divisor between the two, since 2 is already a divisor of 4. But if I think about their prime decomposition, I have 2 squared and I have 2 to the first. So am I taking this min or the max in terms of my powers for GCD? I'm taking the minimum between the two. And for my LCM, I'm going to be taking the maximum between the two. Right? Because I really want it to be a multiple of both. I have to take the most amount of my primes as I can. And I don't take any more so that it's the least of my multiples here, right? If you go back to like our packets that we did in 311, you'll see all of these ideas written out in terms of the primes. But if you get stuck finding the LCMs, you can do it this way, or you could find the GCD and then just do the product divided by the GCD and you get an equation for the LCM as well. So let me scoot this over. Right, this is the same as saying the LCM of 2 numbers. It's going to give me back the product divided by the GCD. So whatever is easiest, whatever is fastest for you, you can use any one of these methods. You can really just find all the multiples and then decide what's the smallest one. You can look at the maximum between the powers, or you can take the product and divide by the GCD if the GCD is easier for you to find. Okay, but any questions on the specific ones that we had here on how we got those values? Okay, and now our goal is to decide, are the permutations even or odd? This has to do with the number of 2 cycles that you'll need to write any one of these. It turns out if you write any of these as a product of 2 cycles, it'll either always be even or always be odd. So regardless of how you wrote it, right, I could have written it in multiple different ways. The fact that it's even or an odd number of them is always going to be exactly the same. So here, if I just look at my 6 cycle, how do I determine if it's even or odd? What do I know for a 1 cycle at a time? Right, so the number 6 is an even number, tells me that the 6th cycle has to be an odd permutation. It's going to be the opposite here. So this by itself is an odd permutation. because the number 6 is even. From that we had that if I just had one cycle, right, it's gonna have the opposite parity here happening. And then, right, we can use this information for all of this, the disjoint ones. They actually don't even have to be disjoint for me to compare what the products look like here instead. But immediately I know that this one is gonna be odd. And so tell me individually, what does my 5 cycle look like and my 1 cycle? Is it, which one is even, which one is odd? They're both going to be even because the numbers 5 and 1 are both odd. So I have even and even here, which tells me what? It's going to be even. I can really think add these together because if I use an even amount for the 5, if I use an even amount for the 1, when I take their product, I really do have that even amount and the even amount for the second. So I can really think mod 2 when I'm adding mod 2. What do I get? Even plus even is 0 plus 0. Should give me back to 0 or my even here. Okay, what about my 4 and 2? Both odd, which tells me what about their product? Yep. What about 4, 1, 1? Odd, and then both of these are even. What does that tell me about the full product? Just odd. Again, I can think add 2 evens and then add an odd. What should you get in those? Or I can think 0s and 1s mod 2 instead. Okay, so I'm not going to check these individually. You guys tell me, what about for my 3, 3? Okay, odd. 3, 2, 1. Okay, let's check. I'll get even, odd, even. This does give me back odd. Okay, my 3, 1, 1, 1. Right, I'll get even for all. I don't care how many evens I get. If they're all even, it's going to be even. Then I have 3 odds, which gives me odd. Okay, 2 odds, 2 evens. Gives me back even. Okay, what about my next one? Odd, and my last one. Okay, so really when I see these ones, these are really signifying like my identities. I know my identity is always going to be even. So I almost can delete these from here and they'll give me the same answer, whatever that leftover is. And really all the ones that are even permutations, so I have an odd number here, don't affect if it's even or odd. What really affects it is how many odds are showing up. And that'll completely determine if you have an odd or an even permutation. So here I have an odd, exactly 1 odd permutation has to be odd. No odd gives me even. 2 odd gives me even. 1 odd gives me odd. 2 odds give me even. I have 1 odd here gives me odd. No odds even. 3 odds tells me odd. Right, and so on, right? So really knowing the number of odds that show up completely determine what happens, because adding by 0 or having an even permutation is not going to change what the parity is there. Okay, so let's decide which ones of these are going to show up in my AN. Really, these are all the structures that show up in my S6. And let's remind ourselves, what is our A6 or AN? What does that represent? This is a set of all even permutations. This gives me back a group. If I looked at all the odd ones, not going to give me back a group because it doesn't have an identity. The identity is an even permutation. So here I can decide of all of the permutations I have, what are the orders that I have showing up for just the even ones for that specific group, right? So I have 5, 4, 3, 3 again, 2, and 1. And let's do some work with our orders here. So for my S6, what should be my order of this group? And how do I calculate it? I had you find that. So I want the order of the group. So I want to know how many elements do I see showing up here. I want to remember these are permutations that go from the set 1 through 6 to 1 through 6 that are bijections. How do I count this? We've actually counted it already. This is going to be my factorial. For S6 is just 6 factorial. If I start with the number 1, I have 6 options on where to go. If I look at what happens to 2, I then have 5 options, and then so on until I get to the last one where I no longer have options. These all give me distinct permutations. They really are bijections here. They're going to be 1-to-1 and onto. So I'm not going to write out the full number. I'll just write out the product here. And then for my A6, what should I have? If I have exactly half of these are even, so that's 6, 5, 4, 3, and actually I'll delete 2 since I'm going to be dividing by 2 here. So in terms of my S6, I have 6, 5, 4, 3, 2, 1 show up as orders. Are there any other divisors that are not showing up as orders here for elements? How else can I come up with a divisor of this number? I could take the prime decomposition, but I can actually do this faster since I already have one product of it. Can I think of one other divisor of this number? Other than 6, 5, 4, 3, 2, 1 that show up here already? What are other divisors that I have of this product? Right, the whole thing. I can really take any one of these numbers, pair them up, or take 3 at a time. So I know I have the number 30, I have the number 20, I have 8, I have 15, all of these that are not showing up in the specific product or as these orders here. So something that we're noticing with our permutation groups that's different from our cyclic groups is that for every divisor, I don't get an element of that specific order. Right, I only had these very specific 1, 2, 3, 4, 5 orders that showed up. Actually 6 because 1 was a possibility here. But right, 30 is one of these divisors that does not show up as one of my orders here. Okay, and let's look at our basics. The possibilities that I had are 1, 2, 3, 4, and 5. I can definitely come up with more divisors of the order of the group that does not show up as the order of one of my elements. In particular, I have 6, right? There's a lot more that don't show up here. So 6 is not in order, but is a divisor. Other things that we can notice is that the highest order I have for my elements is 5 for my even or my alternating group. But for my S6 is 6, right? So the orders that I can have showing up here, if I just look at the even ones, can change kind of drastically on the mins and maxes. I guess the minimum can't. The minimum is always going to be 1, which it always has the identity, so that will always show up as an order. But the maximum might change, or some of these divisors that show up might not show up for the our alternating group here. Okay, so let's look at our recap for our chapter 5. Kind of the most important part is when we have things in disjoint form, this is going to work the nicest for us. We have the most amount of information in those cases. And it turns out that every permutation of a finite set, and we're only going to be working with finite sets. Really, we're only going to be working with things that look like 1 through n. This makes it the simplest, and this gives me all the information for what happens for finite sets in general, if I just relabel them as 1 through n instead of the elements that they have. But it turns out that every permutation in one of these Sn can be written as a cycle, as one single cycle, or as a product of disjoint cycles. Right, being able to write things, and again in disjoint cycles, It's going to give us the most amount of information about their orders, about their inverses, about how to write them as products of 2 cycles as well can be really helpful here. Okay. Right, and we saw if I have a product of disjoint cycles, I just take the LCM of the lengths of each one of those, and that gives me back the order of the product itself. But again, if it's not in disjoint form, we actually saw an example where that's going to give you the wrong answer. So writing it in disjoint form is going to give you the most amount of information. So you want to feel comfortable being able to write it in disjoint form. We had more info. It turned out that every permutation in one of these SNs can also be written as a product of 2 cycles. And we saw an example, maybe something like 1, 2, 3, 4, where I can write this as 1, 4, 1, 3, 1, 2. And this will give me back the same exact permutation, but now written as a product of 2 cycles, which is why when I had a 4 cycle, so length 4 cycle, I needed 3 2 cycles to show up, which is why the length here is going to give me the opposite parity in terms of the permutation versus if it's odd or even. Here I have 4, which is even, tells me that I have an odd permutation because of the way that I can write it as a product of 2 cycles. Right, so that's where that idea was coming from, was because we know exactly how to write them as a product of 2 cycles. I could write this in various different ways. I can put a bunch of identities in between and it still gives me the same exact parity, regardless of how I write it as a product of 2 cycles. If I use an even or an odd amount, it's always going to be the same here. Simon, is that a hand up or just the? No. Okay. Right, which is what theorem 5.5 is saying. If I can express it with an even amount of 2 cycles, no matter how I write it, it has to have an even amount. Same with odd, which is why we can define our permutations as even permutations or odd permutations, right? If I was able to change it, I can't define it. It won't be well defined because it might depend on the way that I wrote it here. Okay, and then our AN is our alternating group of degree n is what we would call it, which has order n factorial over 2 versus my SN, which has order just n factorial. Okay, and then some smaller remarks that we have. If our cycles are disjoint from each other, then they're going to commute with each other. It doesn't matter which order I place them. But if I take something in disjoint form, something else in disjoint form, I don't necessarily know that when I look at them together that they'll be disjoint from each other. So they're not necessarily going to commute with each other, right? So it depends on how I compare the 2 separate elements. If they're disjoint from each other, then they will commute. And we saw a couple examples, or at least one example earlier in the packet, if you want that reminder. But I know thinking like disjoint cycles commute makes you think everything should commute, because I can write everything as a disjoint cycle. But if I take 2 things separately that are not disjoint from each other, which is possible, if I had a 1 showing up in one and a 1 in the other, it's no longer going to be disjoint. I no longer know that they're going to be commutative with each other. Okay, if I take 1 single cycle and I want to find the inverse, I just reverse the order. If I think in terms of bijections, which is what all of these are bijections from a set to itself, the inverse is really saying swap the input and output. And when I read it this way, here's my input, here's my output, and then I repeat, here's my input, the next one's my output. If I want to do the reverse, this now will be my input, and this now will be my output. So my A2 should go to my A1. I'm really reversing all the orders so that I reverse the input and output in terms of my permutations. So in particular, if I only have 2 elements here, it's going to be its own inverse. Because if I write AB, that means A goes to B goes to A. It's the same as if I wrote it the other way around. They signify the same exact cycle here. We have our sock-shoe theorem, which tells us if I have a product of cycles, even if they're not disjoint from each other, I can do this. I reverse the order, and I take the inverses of each piece. So instead of going from alpha, beta to gamma, I go from gamma to beta, alpha, and I take the inverses individually, which means reverse the orders of those elements there. Okay, and then what we saw in our last page there, if I have a K cycle, it's going to be an outright even permutation to not get us confused with the numbers that are showing up. So if my cycle is an even permutation, so it's an AN, that's only going to happen if the K, the length of the cycle, is odd, and vice versa. Right, so they're going to be opposites here in terms of the permutation versus the number, if it's even or odd. And so I also know this is if and only if one of them is false, then the other is false. So this is not even permutation, but it's an odd. And then this would give me back not odd, which is an even number, right? So this goes in both ways. So if I know anything about the length, about what number shows up there, I can completely determine if I have an even or an odd permutation. Oh, and this is what I wrote up earlier. If I have just one K cycle, I can write it as a, oh, we didn't use this word. Transposition is the same thing as saying a product of two cycles. But I did not need to have that there. Right, again, I know I can write this as A1 goes to A2 on the right. Then, then next to it, I would have A1 goes to A3 all the way down until I get to A1 goes to the second to last. And then A1 goes to the very last one here. So going in the reverse order, just like we saw through this example. That's just the general form of how to write it as the product of two cycles here. Okay, and then this last bit is just what we did with the structure type. We can completely determine all the structure types, which tells us what all the orders are going to look like. And if I have an even or an odd permutation showing up, so feeling comfortable figuring out the structure types will give you the full information. So you want to make sure you feel comfortable doing that. That when I add up all the numbers that show up in that structure type, it should give me back that N value, and finding the lengths of these tells me what about the order. I take the LCM between all of them. And if the K is odd, then it's an even permutation or vice versa. And then putting them all together completely determines if it's an even or an odd permutation. Right, so again, having info in terms of disjoint form will give you the most info, the less work you'd have to do, in particular for finding orders. If I don't have it in disjoint form, I'd have to compose this permutation with itself until I get back the identity, and that can take quite a bit of work to simplify. But writing in disjoint form might take a little bit of work, but after you find that, you can completely determine what the order is by just studying the LCMs of the lengths of the cycles there. Okay, questions on our recap? Okay, if not, we're going to look at those discussion problems. There are not that many on here. So we'll go through these together. Okay. So let's imagine we have this beta written in this nice form. And here I have the numbers going from 1 up to 10. I might have some numbers that are missing in between. It looks like I actually have all my numbers from 1 to 10. So I can think of this as a permutation inside of S10. That's really the smallest n I can have working here. Maybe I'll say SK here. But I can also think anything else that doesn't show up, right, is really a fixed element. So I can think of this inside of S11, S12, S13, where anything past 10 that doesn't show up is really a fixed element, right? If I want to say something about the group, I'd have to be a little bit more careful about saying where does it actually live. But if I'm just trying to figure out things about the order, I don't necessarily need to know what K I'm working with, what SK I'm in. All of that information just has to do with how I can write it as a disjoint form, right? That holds all the information. It doesn't care which K value it is. If I had 10, 11, 12, or 13, I can get the same information regardless. Okay, so what we're going to do is decide what is the smallest positive integer n, where beta to the n is the same as beta to the -5. Okay, so what do you guys think we should do to help us start with this problem? What does this start to remind us of, even if it's not directly that? I want to find a positive, smallest positive integer that has beta to the n. What do you think we should do here? What should we study? The order of beta. This is not necessarily going to give me the exact answer, but I know what power will give me back the identity, and then do some manipulation to decide what does that mean about beta to my -5? What should that equal? Okay, so how do I find order of beta? What should we do or check first? So we're asking for the order of an element, not the order of the group. If I want the order of the group, then I have to know what that k value is. But it turns out here, if I want the order of one of these elements, I don't care which k value, I don't care which exact group I'm working in, I will always get the same answer. Of what? So I need to have my disjoint cycle form first. Cycle form. And then we take the LCM of all the lengths. Okay, but we want to be careful. Just because I gave you one representation for that element does not necessarily mean that it's already in this joint cycle form. So how do I check that it's in that correct form? What does it mean to be in this joint cycle form? Let's check this. If each number that shows up in these cycles shows up exactly once, so really in only one of these case cycles. So I'll check for 1, only shows up in the first. I'll check 3, only in the first. The same for 5, 7, 9, 8, and 6. And I only had 2, so I really only have to look at the first and decide is it in the second or not. But if I want to be super thorough, this is technically, we don't have to check this. I can also see this 2 show up in the first, this 4 show up in the first, and this 10 show up in the first. The answer is no for all of them. So this is in this joint cycle form. So I can use the information about these lengths to tell me about the order, but that's technically something I have to check first. Just because I wrote it in this form does not mean that they're disjoint here. So beta is already written in disjoint form. So what LCM should I be looking at for my order? So I need the LCM of 2 numbers. Yep, because this is already in disjoint form. I just look at the lengths of these cycles. And so I count, I have 1, 3, 5, 7, 9, 8, 6. I have a total of 7 numbers showing up in here. So a length of 7 for the first, then 2, 4, 10. I have 3 numbers showing up here. So a length of 3. And so what is my LCM here? 21. Right, these are relatively prime to each other. The GCD is 1. So the LCM must be the product of the 2 numbers here. Or I can take the prime decomposition of both and take the max of the power showing up. Here I have 7 to the first, 3 to the first. The max on my 7 is 1. The max on my 3 is 1. I do get 7 times 3 here for my LCM. So if I had the LCM of 8 and 3, was that the question? Okay, so here I'll think prime decomposition, so 2 cubed and 3 to the first. I want to take the maximum powers. So for my 2, what's the maximum power showing up? Okay, the only other prime I see is 3. What's the maximum power? This is going to give me back 8 times 3. or 24. I can also think, right, these are relatively prime, so I have to get their product. Or I can take multiples of both numbers. So I can take 8, 16, 24, 32, and so on. And I can take 3, 6, 9, 12, 15, 18, 21, 24. And as soon as I see repetition, this is the smallest common multiple. This is going to be my LCM, right? So multiple ways to do this. Study all the multiples and then stop when you have a commonality. So you know you can always stop at their product. That's the biggest that you'll ever have to go. But possibly there's a smaller multiple in common here. Or you can look at the powers and take your maximum between the two. Or you can use your information about GCD if that's faster for you to do, right? All three options are viable to find these LCMs. Yeah. Okay, what if I had done, let's say, 15 and 3. So I want the least common multiple. So 3 is not a multiple of 15, it's too small. I would get 15. If one of them is already a divisor, if one of them is already a multiple, that's going to give me my answer. So between 3 and 15, 15 is a multiple of 3. So the smallest one they'll have in common is going to be that 15. Right. So we want to be careful not to confuse it with our GCD. If I did GCD of 3 and 15, I want the greatest common divisor, and that would give me back my 3. But they really have like the opposite relationships between factors and multiples, between least and biggest here. Okay, so let's try to decide what information does this give me. I know that b to the 21st is the smallest power that gives me back my identity. So I want to decide, how can I use this information to tell me what's the smallest power that will give me back b to the -5? So what can I do here to manipulate it to tell me something about b to the -5? Is there any way I can change this equation to have b to the -5 show up? The reason we'll do that is because I have an identity. So whatever I multiply by, that's what I'll get on that side. And then I want to remember, what does it mean if I have the same base and different powers? What do I do here? We're going to add these powers. So I have 21 plus -5 or 21 -5. On the right again, because I have my identity, I'll just have b to the -5. And so what does this tell me about my power of beta? That gives me back beta to the -5. It's just going to be 16. So 16 is going to be the smallest power. To do so, or else something would have gone wrong with the order of my element beta. Right, let's say I said 15 also works here. But then I can go in reverse on what I did here. And that would tell me that the order of beta was actually 20. That I could find a smaller power that gave me back the identity. Really, these are like taken on the ifs. I can go in both directions to give me this information about a different power of beta, not just my identity here. Okay, questions on this one? Right, so if I ever see smallest positive integer, so that an element raised to that gives me some information, I immediately think my order and then do some manipulation about that, about what I know about the order and what does that give me about what I'm actually looking for in that problem. Okay, if there's not a question, then let's look at number 2. So here we're going to be working inside of S4. And I have my beta and my gamma. And I have very minimal information, but just enough to figure out exactly what am I working with. Here I know what the product of these elements are in both orders. right? So first I plug it into gamma, and then I plug that into beta. That's exactly what I'll get here. Again, remembering these permutations are really bijection, so I can compose between the two, working from right to left. And again, I know what happens in both orders. So the first thing we'll notice is that these are different. So my beta and my gamma can't be disjoint from each other, because if they were disjoint, then they'd be commutative, and you get the same exact result, regardless of what order you multiply them or compose them. So the first piece of information I know is that these are not disjoint from each other. So beta and gamma are not disjoint. If I write them both in disjoint form, they're going to have a number in common, since they don't commute. Or I can think of that conditional statement. If they're disjoint, then they commute. So if my conclusion is false, then my hypothesis would have had to be wrong here. So if they don't commute, then they had to have been disjoint or not disjoint from each other. Okay, the only other fact that we know is what beta, how beta sends 1, or what image of 1 is under beta. I know if I plug in 1 into my function, I'm gonna get back 4. And it turns out this is just enough information for me to completely determine what the 2 permutations are. So I can completely tell you what does each thing send 1 to, what does each thing send 2, 3, 4 to. That completely determines what those permutations are, because I'm working inside of S4. If that was anything beyond 4, I could still figure this out, because if they don't show up, then they have to fix it. I might have to do a little bit more work to say why each of them then had to fix those elements. But let's first try to figure out what can we do specifically with this information. How can I combine it with one of these two to tell me more either about gamma or to tell me about beta here? Okay, so let's look at beta of 1 equal to 4. Okay, so I know what happens after I plug it into beta. And since these are compositions working from right to left, which one can I combine this with? Can I combine info with this one or with this one? Okay, let's see. If I try to plug in 1 into this composition, where do I have to plug it into first? Into gamma, which I don't have information on. So I can think, what does this product send 1 to? I can use the information about beta to actually tell me something about gamma instead. Okay, so let's look. Gamma of beta of 1 should do what? Goes to 2. Right? This whole thing sends 1 to 2. I can just use that cycle notation to tell me what's the input, and whatever's next to it is going to be my output. So I know that's going to be my result. Or I can also think gamma of beta of 1, do the composition by actually plugging into the rightmost, get a result, and plug that into your leftmost. So if I know beta sends 1 to 4, what does that tell me about gamma of 4? If these have to be equal to each other, right? This composition is the same as, right, work with the rightmost and then the leftmost. So have to be equal. So this immediately just told me gamma of 4 gave me back 2. So in the cycle notation, I'll see 4, and then right next to it, I'll see the 2 for my beta. And cycle notation, I'll see 1, and right next to it, I'll see the 4. Okay, so let's decide. What can I do now? Now that I have this extra piece of information, how can I put this stuff together to give me more either about gamma or about beta? Yep, now I can get information about beta, and which one do I look at? The left one, because I want to plug it into gamma first and then plug it into beta. So I first decide What does beta of gamma do to 4? And how do I use my cycle notation to tell me that? So here I look at this permutation, which is this one, and I decide what does 4 get mapped to. I look at the very next number to it in the cycle notation. This is the input, this is the output. So my 4 under this big composition is going to be 3. And then I'm going to take it piece by piece to tell me something about beta, just like I did in the first one. Right, so here, because 4 goes to 3 in my notation, and previously I had 1 goes to 2. And I know this has to be the same as if I did it in pieces instead. So do beta of gamma of 4. So do gamma of 4 first, the inside piece or the rightmost. But this we just said was 2. And so this is explicitly telling me that beta is going to send 2 to 3. So here I have my beta of 2. All of these are equal. The only thing that's outside of these compositions is that 3. So it's telling me that this number is going to get mapped to that one. Right? If these are all equal, I can just think this one is equal to that one as well. Oh, and this should be beta. Maybe that was what you said. Right, so I'm really taking these 2 pieces in my equalities. So I'm going to keep doing this until I completely figure out what all my permutations are. So far, I know beta sends 1 to 4 and sends 2 to 3. So I know what it does to 2 elements. How much is enough for me to know exactly what the permutation is? How many outputs should I know if I'm working inside of S4? Let me think my array notation for my beta. Right now we said 1 gets sent to 4, 2 gets sent to 3. So do I need to figure out both of these separately? Or is it enough for me to just know one more? Right, because this is a bijection, as soon as I know what n-1 of them gets sent to, I know what the last one has to get sent to so that it is actually an injection here. Right, so if I just figure out one more, then I'm good. And in terms of my gamma, same information, but I only know one piece of information. So I still need to find 2 more for that one. Okay, but the work is going to look very similar. Now I'm going to study the fact that beta of 2 gave me back 3. And I'm going to look at gamma composed with beta of this value 2. So here I'm going to look at gamma composed with beta, and I decide what does 2 get mapped to. It gets mapped to 4. And then I study doing these separately, using the fact that I know that beta sends 2 to 3. So all together, what this is telling me is that gamma of 3 gets sent to 4. Okay, so you guys tell me what's the next step. What piece of information do I use, and which composition will I need? Okay, I'm going to look at beta of gamma, and what will I plug in, and what piece of information will I need? Okay, I'm going to need gamma of 3 goes to 4. So what do I plug in into this composition? My what does 3 get mapped to? What do I get here? Right, again, I look at my cycle notation. I find my 3 and I decide what is it mapped to? The thing right next to it. And if it's the last thing in my cycle notation, it goes back to the front. So here the 3 goes to 2. So that full composition will send 3 to 2. And now I look at it in pieces instead. And gamma 3 gave me back 4. So this is telling me beta of 4 will give me back 2. Okay, do I know what my beta is now? Do I have enough information? Yep, so I know my 4 goes to 2. That was this last piece we found. And because this has to be a bijection, every number in the second row has to show up exactly once. The only thing that's missing is my 1. So I've completely determined what my beta is. And in terms of gamma, I have 1, 2 pieces of information. So as soon as I find the third, I've completely determined what that gamma is. So we'll do our last one. And we'll use this last fact to tell us using the opposite order. So gamma composed with beta of this input. And you guys tell me, what do we get? Yep, this 2 is going to go to 3 here. So this is telling me gamma of 2 is going to give me back 3. And if I write gamma in my array notation, what should I get for 1? Right, and it looks like that was the only one that was missing. So maybe I would have saved that one for last. Right, but I know 2 goes to 3 here. 3 goes to 4. 4 goes to 2. And the last piece of information that I didn't have to do all these calculations for was that what 1 gets mapped to, which is going to be my 1. Okay, and let's decide, how do I write this in cycle notation instead of my array notation? Although this way helped me to figure out that last piece of information. So here, I'll start with 1, what this 1 gets sent to. So how do I write that as a cycle? I can omit it. Here I'm going to write them all just so that we can see all the information. But 1's going to get mapped to itself. Means I want it to start and end on 1. Write 1 and close my cycle. And then I continue just to keep it organized. I'll decide what this 2 get mapped to. And so you guys tell me, what does the rest of this cycle notation look like? Okay, and then 4 goes to 2, so I can close it out here. Or I can see all of my numbers showed up, so it would have to close if it was a bijection. What about my beta? How can I write that one in cycle notation? So I'm going to start with 1. We said it goes to 4. That's all my numbers, so it should close. And I can also see that 3 gets mapped to 1, so I can close it there as well. Notice whenever we translate the array notation into cycle notation, it's always writing it in disjoint form, right? So translating this information gives us a lot of info on the disjoint form. There'll be times where we multiply things like in between and then they won't be disjoint. But anytime I just translate this info, it's always going to be in this disjoint form because I'm never going to write back 1 again because I already have that information here. I'll only have repetition if I went back on the info I had already written. Okay, but again, you can delete this piece and it means the same exact thing, but just for us to see fully what these elements are doing. Okay, let's look at our next one. We're going to be working inside of S6. So the permutations from the set 1 through 6 to 1 through 6. And we want to decide how many elements of order 5 are there inside of my S6. So what do you guys think? How can we start this problem here? How can we decide what the elements of order 5 look like? Say it louder. Yep, so however I write these in disjoint form, I'll call this K1, K2, up to KR. The order of this element is going to be the LCM of those numbers. Yep, and can I get one more piece of information that we can get here in terms of these Ks? What do I know? It has to add up to that 6 because I'm going to write all of them, even the the fixed ones that just have a 1 showing up. So I have, right, the sum of all these numbers. So they're K1 plus K2 all the way down to K3. Back 6. This is how I figured out all of my structure types inside of S6. Right, so I need both pieces of information. Oh, and I stopped at 3, but I meant to say R. And this is taking all of them. So I want to decide what are my possibilities for these KIs if I want both of these things to be true. So do I have a minimum or maximum for any of these individually? My KI, what does it lie between? Say it louder. 1 and 6. The smallest K cycle I can have is length 1. Exactly 1 element shows up. The biggest I can have, if it's only a K cycle showing up in the product, will be my 6 here. Right, so the only KIs I can have here are going to be 1, 2, 3, 4, 5, or 6. And I want to decide between those, which ones give me back an LCM equal to 5. Okay, so can we think of any of these lengths so that the LCM gives us back 5 and so that their sum is equal to 6? For this is going to be the LCM of 5 and 1, which is 5. As soon as 1 shows up here, the least common multiple has to be the other number. Right, and my 5 and 1 do actually add up to 6. So both things are true. Are there any other structure types that I can find with both of these properties in mind? Right, so something that that we pointed out is that 5 is going to have to show up as one of our factors for both of the numbers. If it's going to be the least common multiple, 5 has to show up in both. That's not true. A 5 has to show up in at least one of them, right? Because we're taking the max in our powers. So if there's a 5 with a 1 showing up, that 5 will show up. So one of these numbers has to be a multiple of 5. My only options here is exactly the number 5. So one of the KI must be a multiple of 5. So the only option I have is for it to be exactly 5. And so as soon as one of them is 5, I've completely determined the rest of the structure. Since it has to add up to 6, the other one has to be 1. So this is actually the only structure type I'll have that gives me back an order of 5. Right, inside of my S6. So here it turned out that I did actually have to study, or I did actually have to know what this n value was, because I wanted them to add up to 6, right? So that I can find all of the different ways that I can write this. Okay, but the goal was to decide how many of these elements do I actually have. So I need to decide how many options do I have for both of these pieces here, and then multiply them together. And it's actually going to be a bigger number than that. So let's look at 2 different cases. Let's decide what happens to this piece. Okay, remember that the way we write these tells us the length of the cycles, not what number is showing up in those cycles. But what does this represent? I just have a 1 cycle, a fixed element. So I can break this up into cases where one of them is fixed and then the rest, that one is not the fixed one, and then decide how do I count the rest of it. So I'm going to work with 1. So in my first case, I'm going to decide or look at the fact where 1 is the fixed element. And then I'm gonna count how many ways that can happen. And then I'm gonna look at all the ways where one is not the fixed element. Let's look at the first one. So here I know exactly what the one cycle is. It's a cycle that sets one to itself. And now I need to decide, what does the rest of this do? And I'm slowly running out of space here. So I also want to decide, right, I have 5 spots in this one. So I'm gonna put a line so I can decide how many choices do I have for each. The problem is I have multiple ways I can write any cycle depending on what my starting point is, depending on what I said, right? Usually I start with 1 and I determine what the rest of them look like, but I could have started with 2 and completely determine what the rest are. So what I'm gonna do is I'm gonna fix what element shows up first, because I really have multiple ways I can represent this, but I wanna fix this to make it easier to count. So I'm going to just say 2 is gonna be that first spot. I'm not giving you any choices. So I'm gonna put a 1 under this. I have exactly 1 choice for what shows up here. I have exactly 1 choice for what shows up here. And now how many choices do I have for what 2 gets mapped to? Say louder. I have 4, right? I'm starting with S6, and I just said it can't be 2 and it can't be 1. So I only have 4 options, and I can actually see by the dotted lines how many more do I have left. So I have 4 options for the next one. How many for the third? Right, then 2, and then once I figure all these out, that last one does not have a choice. And so I'm really multiplying all of these choices that I have for all of these positions. And that tells me all of the different ways that one can be fixed with this specific structure type. Right, so total here is 4 times 3 times 2 times 1, or 12 times 2, which is 24. So 24 elements of structure type 5-1, where 1 is the fixed element. Okay, so we want to figure out what happens in our next case, and then we're going to add the 2 together. Right, how many did I get where 1 is fixed? How many get where 1 is not fixed? These can never occur at the same time, so I can really add the 2 possibilities to give me the full count. But I'm going to have the same structure type, 1, 2, 3, 4, 5. And which one do you think is easier to start with in terms of the counting? The 5 cycle or the 1 cycle? My 1 cycle. How many choices do I have here? Right, we're starting with S6. So yep, I have 6 total options, except now I'm in the case where 1 is not the fixed one. So I actually have 5 total options for this one here. Anything but 1. And now, just like the last one, I'm gonna fix what the first element is, so that I don't have to be careful about the different ways that I can rewrite the same exact cycle. So I'm going to force the first one to be 1, because that's the only thing I know for sure is not showing up here, right? If I would have written 2 here, I would have an issue if my 2 was showing up here as well. Okay, and so now I just want to continue and decide what are my options going forward. So for my second number, what is my option? How many options? I have 4, 3, then 2, then 1. And so all together, the total here is 5 times 4, 3, 2, 1, which is the same as 120. So if I want all of the elements in S6 of order 5, I'm going to add up these 2 numbers to give me 144. This is my final answer here. All right, break it up into cases where they're disjoint from each other to make it easier to just add up all the possibilities. And then within those, if these were kind of complicated to count, I could make smaller cases for those as well. But it turned out as soon as I know what the first number is that shows up in the cycle notation, this is the only way that I can write this. Versus if I said 4 show up here, then there's multiple ways that I can rewrite the same exact cycle if I had started with this one or that one or this one or that one. Right, so fixing that first element that shows up makes the count a lot easier to work with. Okay, questions on this one? We end at 50, is that right? Oh, that's it.
No, 144 is only.
Inside of S6 in particular, if I had changed what the 6 was, I could possibly gain more elements of order 5. I could possibly gain different structure types that gave me back the same exact LCM, right? I could have had something like 511 that was inside of S7, or if that was an S10, I could have had 5 and 5. So here it really does matter, right? What the end value is here. If I want to count the total amount, if I just want to decide the types of structures, it's not quite as difficult, or just finding the order of elements. I don't need to know where it's from, but if I want to count how many I have, it really does depend on that end value that I have here. Yeah. Okay, anybody else before we look at our next one? Okay, so this number 4 is actually a homework problem. So I'm just going to get us started on these so that we feel more comfortable. I think this is the only proof that shows up on the homework. One of them says explain, so you don't have to do a full proof on it. And then this one is about subgroups. So I want to make sure we get some more practice on these, especially because we've done so much work with writing them in terms of cycle notations. We want to also understand these are just permutations. These are just bijections. What information can I take from them? Right, I don't always have to write them in cycle notation. Lots of times this is more helpful. But here in particular, thinking about them as functions will give us all of the information. So let's look at our set. H, it's taking the elements from S5. So bijections from 1 through 5 to 1 through 5. So if I look at beta, 2, 3, 4, 5. So 1, 2, 3, 4, 5. Where this is a bijection. So we want to remember injective and surjective. Since they're the same exact size, they're really the same sets here. That's saying that every codomain element has to show up exactly once as a range element or as an image, right? It has to get mapped to exactly once if I want both of these things to be true. Okay, and our goal is to prove that this set, where I'm only looking at the bijections or permutations here, that send 1 to itself and 3 to itself. So it's saying all the other outputs, I don't care what it does, I just want it to be a bijection. So I have no restrictions on what 2 does, what 3 does, what 2 does, what 4 does, or what 5 does here, right? We have choices on what could happen for those 3 outputs. Okay, our goal is to show that this is a subgroup of S5. So what should be the very first thing that I do in any one of my subgroup tests? And I'm going to call the 0, right? This is what I want to show for every single subgroup test, is that I have a non-empty subset. Okay, so which one of those 2 pieces is the easier one to prove or to state immediately? Subset. Right. By definition, I'm only looking at elements in here with an extra restriction. Right, so immediately I know is a subset of H, of S5. And then what's our common way to show that it's non-empty? Show the identity, and in these permutations, I use my curly E for my identity. You can use little e if you want. We want to show that this is inside of H to show that this is non-empty. So the first thing we need to understand is what is the identity element in the big group, and how do I show something is inside of H? So what is the identity in F5? So here I can think identity function, which fixes every single element, or in my cycle notation, right, I would write 1 goes to 1, so 1 cycle here, 2 goes to 2, 3 goes to 3, 4 goes to 4, 5 goes to 5. That's the same exact thing as every element getting sent to itself, or where X gets mapped to X, right? A regular identity in terms of functions. So everything fixed, which is the same as thinking if I plug in X, I should get back X for everything inside of my domain. Okay, do I know this element is in there? How do I check this element is inside of my H? Right, so here beta is like my dummy variable. If I want to check something is in there, I replace my betas with the specific element I'm working with. So I want to check this 1 goes to 1, this 1 go to 1, and this 3 go to 3. If I can show both, then I'm done. But this is telling me no matter which X I choose, it'll get mapped to itself. So in particular, if I plug in 1, I do get 1. If I plug in 3, I also get 3. So this is one of my permutations that lands inside of H. So this is a non-empty subset. So I've done my part 0 that I need to do regardless of which subgroup test I use. Okay, what would be my next step? And we won't do the rest of these, but just to set you up. So we actually have multiple options here. This is the first time where we can actually use the finite subgroup test, because all of my S5s, or excuse me, SNs are finite. They have order n factorial. If I take any subset, it also has to be finite, right? It can't grow if I'm a subset working within here. So I could use my 1-step test, I could use my 2-step test, or I can use my finite subgroup test. So all subgroup tests are available. But the fastest here is going to be the finite subgroup test. What would I have to show for my finite subgroup test? What's the only thing? This one only requires one thing. Yes, but one condition will give us the full information. So let's remember 1-step tests, A, B inverse. So it does the product and inverse at the same time. 2-step test does them separately, show it's closed under the operation, and then your inverses are in your set. And for my finite subgroup test, I only have to do one of the two. Do I show closure or do I show inverses? Closure. Here, if I just show closure, this immediately implies that the inverses are also in there. It's not as obvious, right? We'd have to go back to the proof to see why closure completely tells us that the inverses have to be there. But this saves us some work. I now just have to show if I take two things in H, when I compose them together, it's also in H. So it has those nice properties that 1 gets sent to 1 and 3 gets sent to 3. But if you want to do a 1-step or a 2-step, that'll make you work with inverses, which might help you understand, right, in terms of functions, what do your inverses look like, what properties do you know there. But your choice on which one of the 3 you actually want to do there. But the finite subgroup test is going to be the fastest because you only have to show the closure part. Did you have your hand up? Okay. Okay. Anybody else? Okay, so I'm just going to set us up for the next packet, but we're not actually going to start it today. We'll start that on Wednesday. So the next thing we're going to do is talk about maps between our groups. And we want these maps to have a little bit more structure because we really wanted to preserve the groupness of these groups that we're going between. Unlike with our sets, if I just did a function between, I really don't have any other structure on my set, so I can work with all functions. But here we're going to work with specific functions with this extra property that it somehow preserves the fact that we're working with groups. Okay, so we studied our permutation groups really because all of our finite groups are essentially going to look like a permutation group. So a subgroup of an SN, right? I don't know exactly which one it is, but I can completely look at all of my finite sets as one of these permutation groups. So permutation groups tell us the full info on what finite groups look like. But the thing we need to study is, what do you mean by it looks like or is essentially the same? So here, what we'll mean by this is after we rename the elements and the operation, the Cayley tables will look exactly the same. The way the elements operate with each other will be the same between one group and the other. We really would not be able to tell them apart after we just rename the elements and the operation. And what we'll say is that those groups are going to be isomorphic to each other. But before we talk about isomorphic, because really what we'll see is that we can find a map that's a group homomorphism and bijective is going to be isomorphic. We'll first talk about a group homomorphism to get a better idea of what that'll look like, to see what do we actually mean by preserving the structure, what would we need between the two. So on Wednesdays, beginning of Wednesday's class, we'll start with our definition of group homomorphism to get these relationships between these groups, how they interact with each other, so we eventually be able to determine when are groups pretty much the same or different? What properties about them have to be the same if I want to think of them as the same exact groups? Things like orders of the group, orders of the elements, things about their inverses, the way you multiply elements together should look the same, because really if I think Cayley table, which has all the info, after I rearrange the order, the Cayley table should look identical to each other. After I rename them, that's really telling me I have the same exact groups, just named differently. Okay, but we'll start with that on Wednesday. So if there are no questions, I'll see you guys then. Have a good one.